I'll share my screen. Is everyone able to see my screen?
Yes.
Yeah, okay. All right. So we are going to start windowing today. So a quick recap about the FFT analysis that we did. This was our LFP signal, one trial of the LFP signal, and this is what the FFT looked like. This is the amplitude of the FFT, 4096 points corresponding to the 4096 data points here in the time domain. It's symmetric about half the sampling period, which is a property for any real signal. If it's complex, it doesn't hold, but for any real signal, the amplitude is symmetric. This is the same thing on a log scale, the same plot as this. We got the frequency axis like this. So then we notice that it's between 0 and 2 kilohertz, like so, again in the log scale. And even though it looks not much informative for a single trial, if I average the log amplitude of the FFT over 76 trials, I end up getting something like this. Okay, and if I zoom out, I'll see that there's this uh, nice sharp peak at 100 hertz corresponding to the monitor refresh rate. And it has this nice 1 by f roll off, which is true for any biological signal. A lot of power at lower frequencies and very little power at higher frequencies. Note that it's a fall off on a log scale. So from 5 to down to almost 3, it's a 100-fold change in amplitude um, as you go from 0 to 200 hertz. Okay, and then we noticed that the Fourier components here are essentially the for the entire signal, this entire signal. So if I want to know what's happening only at between, let's say, 200 to 400 milliseconds, I need to compute the FFT over only that segment, which is what I have done here, which is shown in red for only 2 to 400 milliseconds. However, the frequency resolution depends on the duration over which you compute the FFT. It's in fact given by 1 over T. So if you only have 200 milliseconds, your frequency resolution is now 5 hertz. So the dots here are much more spread out than the dots here. Likewise, this 100 hertz component, which is so nicely captured here, is not as prominent here. As you can see, there is a bump, but it's no longer as prominent as it was earlier here. Okay, and based on this, we can say that there is an oscillation at around 50 hertz here, and there's a suppression at lower frequencies also, which is a very typical response when a stimulus is presented. Okay, there's always a suppression at lower frequencies, and if the stimulus is appropriate, you might see an increase in power at gamma frequencies. Okay, so before doing this windowing, I will go back right now and do a little exercise here. This is how we were playing the, learning about Fourier analysis by writing small codes. Okay, so let's look at this little code. This is the same program that I had emailed. By the way, did you guys get the email that I sent?
Yeah, yeah.
Okay, so everybody got this FFT practice.m mat file, sorry, M file, correct?
Yes, sir.
Yeah, okay,
Yes.
wonderful. So here's a small exercise, and you will see how interesting it is. Just and we are going to look at only like 15 lines of code here. So the sampling frequency is 1000 hertz. The duration of the signal is 0.5. Okay, so my FFT will have 500 points. So when I do compute the FFT, what's going to be the frequency resolution?
Frequency resolution is 1 by T, right?
Very good. 1 by T. So it's going to be 2 hertz.
Yeah.
Right? So T now, this is the time vector, has 500 points going from 0 to 0.999. And YS, which is my frequency axis, also has 500 points going from 0 to 998. Okay, so the frequency resolution is 2 hertz. I'm sorry, this is time. And this is frequency. First value is 0, then it's 2, then it's 4, and so on. Okay, so this is straightforward. Let me look at a sinusoid at 50 hertz. So I create a sinusoid at 50 hertz, and I'm going to plot the sinusoid and the absolute value of that. So here's what I get. This is not surprising at all. So this is a 50 hertz sinusoid. So in 500 milliseconds, you should get 25 cycles. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess if you count it, we will see there are 25 cycles. And in the frequency domain, this is a nice sharp peak at exactly 50, and it's 0 everywhere else. Okay, and it's symmetric. So you see another peak also at 950. So this is what it is. Okay, that's very good. But now I ask that suppose I have a sinusoid at 51 hertz. What do you think? So let me just do a hold on here. So hold on and let me plot this. So this is that sinusoid. Okay, so it's slightly faster. So you can see that the cycles are, this thing is coming earlier. This orange is the 51 hertz. So my question is, what do you think is the Fourier transform of this signal going to be? Anyone?
Frequency.
Yeah, so you would think that, okay, the peak should just shift to 51. But now the problem is that you are only looking at the frequencies values that are separated by 2 hertz. So you've got a point at 50, the next one is at 52. Because I'm only looking at half a second. So there is no 51 hertz component here at all. It's either 0 or 52. So can I create a 51 hertz sinusoid using all frequency components between 0 to 48 up to 1000, which doesn't have 51? Sure, I can do it, but I'll need a lot of frequency values. Now, if I look at the 51 hertz sinusoid, this is how it looks like. And let me just zoom in here between 0 and 100 so that you can appreciate the difference. This blue is a nice sharp peak and 0 everywhere else for 51 hertz, which is actually between 50 and 52. But I don't have that frequency here. My resolution is only 2 hertz. So I need a bunch of these sinusoids. When I add these sinusoids together, with after scaling with their amplitude and shifting with the phase, which I'm not showing here, I will get a 51 hertz sinusoid. I will be able to recreate the orange trace here perfectly, but I'll need so many different frequencies. Okay, so it's a little bit surprising. Let me run a for loop here so that maybe you guys can appreciate this better. Suppose I go I equal to 1 to 20 and then sine a 2 pi it, subplot this, subplot that, and I'll pause here. I guess I'll display what I is, pause, clear the figure, and then do this. And here let me just do xlim between 0 and 30. Let's say 0 and 50. So let me run this. It's going to create sinusoid at 1 hertz, 2 hertz, 3 hertz, and so on. Plot that signal and then plots its Fourier transform. So if I run this, see, this is a sinusoid at 1 hertz, but it's only half a cycle here. You don't have a full cycle. It's only half a cycle because you only have 500 milliseconds. You are not looking at it for 1 second, which would have produced a full cycle. So you can't have a peak at 1 because there's no 1 hertz component. It's only 2, 4, 6, 8. And you need many components to represent this properly. You need a 0 hertz. You can see this peak at 0 and 2. Now, if I move forward and make it 2, now it's a full cycle. So now the peak is only at 2 and is 0 everywhere else. Okay, and for odd one, you will see that it breaks into many components, and for even ones, it becomes a peak. See that? Quite neat. The maximum here is 250, which is, as I had said, n by 2. So otherwise, it's coming down to a lower value because all of them will have to add up to this. So if you need multiple sinusoids, you are going to have lower amplitudes here. See that? Every even one is good, every odd one is off. Okay. Yeah, is there a question here?
So first of all, I want to know whether you have given any quote. Like, I'm like little amazed by the way it is being the 51 hertz or the odd frequencies are represented in the even frequencies.
Hmm.
So
Yeah, it is amazing. You're right that it looks odd that you can represent a 51 hertz sinusoid using only even sinusoids. But the truth is that you can do it, and that's what we had learned in the previous few lectures, that you can always recreate a signal of length n using n Fourier coefficients. That's the DFT. Okay, and the reason why this is happening is that 51 hertz is actually not orthogonal to 50 hertz or 52 hertz when the duration is as small as 500 milliseconds. Okay, so one logic that is given that, hey, sinusoids at different frequencies are orthogonal, but they are only orthogonal when you integrate over an infinitely long duration. Then any two sinusoids are orthogonal. But when you are only looking at half hertz, so see, let me just show you this one again. This is a 1 hertz sinusoid observed between 0 to zero point 0.5 seconds. Now, if you ask, is this sinusoid, does it have a 0 hertz component or a DC component? Now the answer is yes. The answer is yes, because it's always positive throughout this 0 to 500 millisecond interval. If we had looked at an entire cycle, 0 to 1 seconds, then it would have zero DC component, because the positive that you're getting here gets cancelled out by the negative that you will get between 0.5 to 1 seconds. But if I only observe half a cycle, so it will have a non-zero DC coefficient, because it's always positive. So if I can, so that is why this 0 hertz component here is large, and so is the 2 hertz component, but then it sort of falls apart. Okay, so it's important to realize that sinusoids are only orthogonal to each other, which means that you will only get a peak where the sinusoid is at and nowhere else in the Fourier spectrum. This only happens if the sinusoids are viewed for an infinitely long duration. Otherwise, you can actually project any sinusoid of any frequency on a fixed set of sinusoids of certain frequencies. If I look at these the Fourier coefficient sinusoids that correspond to this, the 0th hertz sinusoid is a flat line. The first coefficient, which is the 2 hertz sinusoid, is one cycle in this 500 millisecond interval. It's one cycle within 500 milliseconds, so it's 2 hertz. The next Fourier coefficient is at 4 hertz, which will have 2 cycles, then 3 cycles, 4 cycles, 5 cycles, and so on. So all these Fourier coefficients, the sinusoids, are all orthogonal to each other, right? Because it's one cycle and then 2 cycles. If you take an inner product, it will be 0. But the other sinusoids, the fractional ones, like 1 hertz, 3 hertz, they are not now orthogonal to these. So you can represent a 1 hertz sinusoid as a linear combination of 0, 2, 4, 6, 8 with these amplitudes as coefficients. It's an important thing to realize. Okay? Does that make sense?
Yes.
Okay. Yeah. So now the question is that, okay, I wanted to look at a 3 hertz sinusoid, and when I do the Fourier analysis, it looks a little odd. It has got lots of coefficients. So why is that happening? And I gave you an answer here, but let's think a little bit deeper about what is happening here. So okay, let me actually give another example here, which is probably easier to understand. Suppose I'm saying that this is my t vector. So if I plot t, this is how it's increasing, right? From 0 to 0.5, it goes slowly. Now, if I think of a signal which is very slowly changing, see, from one point to another in the time domain, the change is very small. It's a very smooth function, correct? So what do you think is the Fourier transform of this signal going to look like? It's a signal that's drifting very slowly. Right? So it's like a small, from 0 to 0.5 seconds, the signal has taken a value between 0 and 0.5 here. So if you think of a signal like this, it's always drifting very slowly. So you would argue that the Fourier transform here shouldn't have any high frequency components. It should only have very low frequency components, because after all, it's drifting very slowly. Let me in fact make it also a zero mean signal. So So if I plot it like this, mean of t, so it goes from minus 0.25 to 0.25. On average, it has a value of 0. If I integrate this signal, I will get 0. My question is, what is the Fourier transform of this signal x given by t minus mean of t? And you would argue that this signal shouldn't have any high frequency component because I'm never seeing any big jumps in the signal at all. It's always changing very slowly. Correct? But let me look at the Fourier transform. So I look at plot abs FFT of x. And to my surprise, I see lots of high frequency components. See, this is how it looks like. It has power up to like 100 hertz, 200 hertz, and so on. Just to exclaim from 0 to 500. Oops. So to represent this very slowly moving signal, you need so many frequency components. At 0, it is 0. Notice that the first component is 0 because the DC value is 0. But then you need so many frequency components. The question is, why is that? This signal never seemed to change too much. There were no sudden jumps. So how come you need so many frequency components, even at higher frequencies, to represent this signal? It's a very deep-rooted question. Okay, and there are no stupid answers. So let's have some answers. Think and tell why you think you need such a large number of frequencies to represent this signal.
Um, I can just give a attempt. So
Hmm.
in time domain, it's so since it's increasing smoothly. So if we take an individual coefficient and then add it up, so we can get that we need a higher amount values of coefficients so that we can obtain the uh, time the plot which we have obtained in the time domain.
Yeah, no, so that's the mathematical answer. The mathematical answer is that yes, if you have all these coefficients and you generate sinusoids and you add them, you will get a slowly moving signal like like this. So that's correct. That's the mathematical answer here. My question is, physically looking at this signal, this is a signal which doesn't seem to have any jumps or any. So remember, the fast components in a signal, faster frequencies come about when the signal suddenly changes. Here I have got a signal that doesn't seem to change at all. I mean, change very slowly. So how come its representation, the frequency domain, has very sudden jumps? So you're on the right track mathematically, but I'm looking right now for a sort of physical intuition here.
Okay.
So anyone else? Just try. I mean,
Uncertainty
difficult question.
principle.
There is no uncertainty principle here per se. Think about, this is a hint now, think about what you are actually doing to this signal when you are computing the DFT of it. When I compute the DFT of a finite length signal, what am I actually doing there?
Limiting it to a particular time interval and then re-sampling. No, sorry.
No, but yeah, so it's you're on the right track. Yes, so I've got a signal like this, which is increasing from minus 0.25 to 0.25. What do I create something out of this finite length signal, and I look at the discrete Fourier series coefficients of that.
Yeah.
You make copies of it. You make an
You
infinite.
make copies of it. That's right.
Yeah.
Okay,
Those
so
are correct.
now, so think about it. What I'm looking at is a slowly moving signal, a small drift in the signal. Of viewing this signal for an infinite duration, it would have been a very slowly drifting signal without any changes everywhere. It will slowly go from minus infinity to infinity. If I had the luxury of looking at this signal for an infinite long duration, but because I don't have the luxury there, I'm actually making infinite copies of the signal, which means that actually the signal that I'm creating out of this, let me just try to draw this here. Is this. Okay, so this is minus 0.25. Oopsies. And this is 0.25. I looked at one cycle here, but I'm actually making an infinite copies of this, right? And here's a huge change in the signal. This is not there in the original signal. If I had the original signal and I had viewed it, it would have been something like this, probably. But I don't know because I am only access to the signal between this duration. And I am actually creating another signal which has an infinite number of copies. So this other signal that I have created, the periodic signal, now has a sudden huge jump. And this is going to introduce a lot of high frequency components in the signal. Okay. And this is my own doing. I mean, this is because I don't know what the signal is outside this duration. I don't know how it behaves. So I'm going to make certain assumptions. And this is the assumption that DFT makes, that you are going to just make copies of this. And this sort of ruins it. The actual, even though there are no high frequency components between this interval, between this line, they're all moving slowly so that between any two time points, the signal doesn't change much. In the periodic version, there are sudden jumps, and therefore you need a lot of high frequency components to represent this. Okay, does that make sense?
Yeah.
Yeah. So that's where this windowing business comes in. Okay, so this is a quick recap of the windowing, what I just mentioned. We have just done it in the previous classes. So, this is DTFT, right? So this is an aperiodic signal, and this is DFT, discrete Fourier transform, which are essentially just the samples of the DTFT at 2 pi k by n, right? So I get these sequences. But the DFT is actually thought of the DFS, the discrete Fourier series coefficient of a periodic signal that is created by making infinite copies and translating them of the original signal. I'm just I'm just saying this again, but we have just done the same thing in a couple of classes ago. So we can just quickly do this. This is a periodic signal. So if you now think, you ask, what is the difference between the actual spectrum that the signal may have and the spectrum or the Fourier coefficients that I'm actually seeing. Okay, what's the difference between the two? So the answer is as follows. This is just again, I'm just talking about discrete Fourier series here. So the answer is as follows. To make a finite length signal, you can think of that I am actually having a infinitely long signal, but I am multiplying it with a rect function, which takes a value of 1 between 0 and n and is 0 everywhere else. Okay, so if I go back here, think about this. This is what I'm trying to impress here, trying to suggest is that whether or not you like it, you are always looking at a signal which is multiplied with some window when you look at a finite length signal. Okay, so I've got a signal like this, let's say, and it's infinitely long, and the Fourier transform of this is what I'm interested at. But suppose I just gave you a signal between this interval. I just gave you this signal, this much. So you don't know what the rest is. You don't know what's here. You don't know what's there. You didn't have the luxury of viewing this signal for an infinitely long duration. Nonetheless, you want to know that if I look at only this and I try to create a frequency representation of this, how is it related to the frequency representation of the entire signal? Okay, and the answer surprisingly is not very hard, because what this new signal is just a multiplication of the original signal shown in red multiplied by a rect function shown here in green. If I multiply this, I'll get this modified signal, which is 0 everywhere, and then it takes this sort of a waveform and then it becomes 0 again. Correct? This red multiplied by this thing is this finite length signal that you have. So in the frequency domain, it's nothing but the actual signal, actual Fourier transform that you interested in, convolved with the Fourier transform of the rect function, which, as we know, is a sinc function. Okay, does that make sense? So the distortion that we are talking about is a convolution with the Fourier transform of the rect function, which is this. So even when you think you're not multiplying the signal with anything, any other window, you are actually multiplying the signal with the default window, which is a rect function, whose Fourier transform looks like this, the amplitude of the Fourier transform. This is just the sinc function that we have seen earlier. And you are going to convolve your Fourier transform, the true Fourier transform, with this thing, which is going to distort it. And there's no way around this. You can't escape this. Okay, so when we simply take the endpoint of a sequence and applying the DFT, we are actually multiplying the signal with a rect function. In the frequency domain, it amounts to a convolution with the Fourier transform of a rect, which is a sinc function, which looks like this. Now, what this means is that if I have a frequency which is sitting, let's say, exactly, so if I have a delta function sitting at some frequency. Okay, it's a perfect sinusoid. When I convolve it with a rect, it's going to just put this thing here, which means you will not only have power at that frequency, you will also have some power at nearby frequencies. This is what is called spectral leakage. This is actually, not it's a technical term, which means that if I've got energy of a signal at some frequency, because I'm viewing it only over a finite duration, some part of it is going to just leak out to neighboring frequencies, to the side bands here. Okay, and this is spectral leakage, and it's just because you only got to view the signal for a finite duration. So you can't actually pinpoint with absolute accuracy where the frequency is. It's going to have some region around that frequency that's going to sort of light up. Okay, and this spectral leakage is unavoidable. However, now that I'm telling you that every signal gets multiplied by some function, default being a rect function, I could choose to multiply the signal with some other function, which is called a window, in the hope that this spectral leakage can be reduced. So if because I'm always multiplying the true signal with some function inherently when I look at the discrete Fourier transform, I can say, hey, let me multiply it with a better behaving function, because this rect function is very harsh. It has this very sharp change in the signal. It's 0 and then suddenly it becomes 1. So you need higher frequencies to represent it. So the side lobes are actually quite large for a rect function. If I instead multiply it with another function which is more well behaved, maybe the higher frequencies will be less. Okay, and this is a trade-off between, in general, it comes as a trade-off between the width of the main lobe, which determines the resolution, and the height of the side lobe, which determines the leakage. Okay, and turns out there are a host of different functions that you can use as a window. If you first think about it, it looks very, very strange. I will show you the example that we were continuing. Why on earth do you want to multiply my signal with, let's say, a Hanning window, which looks like this? The Hamming end is this one, Hanning is one. So signal processing people just keep coming up with newer and newer windows that have different properties. We won't get into the properties of windows too much in this course. You can actually have an entire course on how to design filters and how to design windows. But as you can see, there are a bunch of these windows that you can pre-multiply the signal with. And essentially, it boils down to taking the convolution with the Fourier transform of the window, which for different windows look different. So for example, if I have a Hamming window, I have a much bigger main lobe than a rectangular window. This, by the way, now is a log scale. So it's a 20 dB or a 60 dB shifted, it's actually on a linear scale quite low, but on a log scale, it's large. Notice that the rectangular window has a smaller main lobe, but the side lobes are much bigger as compared to a Hamming window or a Hanning window here. Which means that you are going to have poorer resolution, but you are going to have much less leakage if you pre-multiply the signal with a window like this. It's actually quite interesting. If I compare a square window, a rectangular with a Han or a Bartlett or a Welch, don't worry about the names. The concept is important. You're going to have a smaller main width here for a rectangular window, but a lot of spectral leakage. And I can minimize the leakage by multiplying the signal with something else, which will increase the main lobe, but will minimize the side lobes. Okay, because these signals, these windows change slowly. So there are no sharp jumps like what we had seen in a rectangular window, which had these sharp jumps. These are very gentle windows. Okay. So let me go back and actually show you this in action. This is where, as I said, playing with MATLAB becomes so useful. See this, all of what I have told you today can be understood with only like 10 or 20 lines of code. You know, so let me go back, and so remember, this is my time domain signal. Later here. This is my t going from 0 to 0.5 seconds, taking values between minus 0.25 to 0.25, right? Now I can, let's say, create a Hanning window of length n. It's a simple command here. H is equal to Hanning n. The window, so hold on, plot H, plot TH. This is what the Hanning window looks like. So essentially, I'm saying that I'm going to multiply my original signal with the Hanning window, and that is going to just look like H dot star T. Oops. Oh, that's a wait. So H is a column vector. So that is why you guys saw that. If I plot H, this is the window. Plot. Yeah. So this thing here is actually the distorted signal obtained by multiplying the original signal here with a Hanning window. And I'm sure that first time then when you see this, the question that comes to the mind is that why on earth should I distort my original signal, which looks like this flat line, with something that looks like this? This seems to bear no resemblance with the original signal here. Okay, so the original signal is shown in blue. I am multiplying that signal with a Hanning window, which looks like this. And the resultant signal, it's a dot product here, point by point product, looks like this. And first time when you look at it, you will say that, hey, that looks like a bad idea because it's just going to change your spectrum. But the truth is the spectrum is changed regardless. Whether you like it or not, your spectrum is always changed, because remember the original signal, which was not moving very, was changing slowly, was having these large jumps when you made a periodic copy of it. This other signal shown here in yellow won't have those drastic jumps because it starts from 0 and ends at 0 always, because the window starts at 0 and ends at 0. So in the new signal, which is made by doing infinite copies of this windowed signal, actually won't have those large jumps when I make copies of it. And that is going to reduce the frequency components at higher frequencies. Okay, are you guys following this? This is very important. This is the essence of why we do windowing. Let me show you the Fourier transforms. Plot ys abs FFT x. It's quite awesome that you just have a single command for this. I'm just going to plot this, and then let me just do stem here. Stem shows everything. Yeah, and let me xlim between 0 to 100 hertz. So this is the original signal, which shouldn't have the high frequency components, but it does. What happens when I look at the, so hold on. What happens when I look at the Fourier transform of the distorted signal, the windowed signal? This is a dot product which with H. This bar here just converts it to a uh, row vector. So I can take this is a row vector, this is a column vector. So I just made it a row vector. That's it. Now, if you look at it, what you find is that these high frequency components have been reduced quite a lot. And that's because that sharp sawtooth like change is now gone. Okay, so now you don't have high frequency components. You are in some ways capturing the true thing, which is that this signal didn't have any very fast components. So it's actually constituted by only small changes, only lower frequencies. Actually, let me show you the sinusoid, and then it will probably make sense more. So remember, if I create a sinusoid at, let's say, 51 hertz, so I create a sinusoid at 51. I'm plotting that here. That's my 51 hertz sinusoid. And this is the abs FFT of this. I do xlim between 0 and 100. 0 and 100. This is the 51 hertz sinusoid, correct? Remember, and it has all these high frequency components. If you look at this signal, you can figure out what is happening. Okay, so the signal here was going up and coming down, going up and coming down. If it had an even number of cycles, then it would have been coming up like this and finishing up right here, so that when you again put another copy of it, it's like having the same sinusoid repeated. This would have been the case had it been a 50 hertz sinusoid. But because it's 51, it's got half a cycle extra here. Now, when I create multiple copies of it, it actually would look like this. One cycle, two cycle, and then you've got a half cycle, and that's your signal. When I make copies of it, it will have this weird edge. And this is high frequency stuff. This is why you need so many frequencies, including higher frequencies, to represent this signal. Okay. That is why you have so much of this. Now, what happens when I multiply this signal with the Hanning window? So let me just do that. I'm going to now hold on here and plot t comma x multiplied by with the Hanning window that I had. This is my signal now. It's multiplied by a Hanning window. And you might say, hey, it looks odd, but it's there for a reason. It's making sure that the signal is starting at 0 and ending at 0. So when I make copies of it, there are no sharp transient at the edges. And now if I look at, hold on, the Fourier transform of this by S absolute value of the FFT of this is how it looks. Okay, can you guys see the difference here?
Yes, sir.
It's quite amazing if you think about it, that if you multiply this original signal with something that seems to sort of take it away from what the truth is. Remember, what is the truth here? The truth is actually a single peak at 51. If you had the luxury of looking at this signal for an infinitely long duration, which means you would have an infinitely dense packing here of frequencies, right? If you look at it for an infinitely long duration, then your frequency resolution is going to be essentially, zero, right? So you'll have a continuous spectrum and you would see a single peak at 51. That's the truth. That is what you want to see. But you can't get to that because you have only viewed the signal for 500 milliseconds. So bad luck, you only have that much and you have to make do with that. And if you just take the Fourier transform, discrete Fourier transform for 500 hertz, this 500 millisecond signal, what you end up getting is this blue thing here, which is all over the place. This is spectral leakage. This stuff here is spectral leakage. Okay, and that's just because even though you don't think that you haven't actually done anything to the signal, you have actually multiplied it with a rect function. The rect function has sharp edges and it's distorting your the frequency representation. It's producing these side lobes. So I'm actually better off multiplying it with the function, make sure that there are no funny edges, and it actually gives a frequency representation which is closer to the truth, and it has a peak at 50 and 52 and then it falls off, but nothing at other frequencies. This is the power of windowing. Any sort of window not only changes the absolute value of this spectrum, but also the phase of the signal. You have changed the signal. So it's going to distort the original phase, it's going to distort the amplitude, and the different windows that we talk about, the Hannings and the Hammings and the Bartlett and the Welch, they all have different properties. Like, for example, a Butterworth signal that we actually use, it has a linear phase, which means that it's almost as if you have got the original signal, you multiply it with a Butterworth window, and the distortion in the frequency domain is such that the phase shifts linearly with frequency. So in the time domain, it's just a translation of a signal. It has this concept called group delay, which I will introduce in the coming lectures. That group delay is more or less constant for a Butterworth filter. So the reason we have a family of filters is because they have interesting properties that are handy when we look at the signal in the frequency. Unfortunately, it's a course in itself. Okay, so I can't get to this, but the gist of why we do windowing is what I am explaining today. I hope that makes sense. Okay, and while we are at this MATLAB, there's a nice command called WV tool. So It's a GUI that displays the signal and its frequency domain representation. So you could play around by, do you have a button? You can create windows and you look at the window here and it will tell you what different, so this is a Bartlett window and you can easily see what it's how it's distorting. This is the frequency Fourier spectrum of the window. This is the distortion that you see in the original signal. Okay, so as before, it's very useful to actually play with MATLAB. Okay, this windowing, these are very deep concepts, not straightforward at all. But you actually learn a lot just by playing with the signal and doing little manipulations here. Just multiply it with something, see what happens. And that way also you learn a lot. Okay, and that's the approach I'm sort of championing here. Please do it this way while you are also doing the assignment, which will give you the theoretical edge. Okay, so both are very handy. So this window, there's a whole GUI that is present. There's a windowing toolbox or something. If you do doc WV tool, it will tell you what are the other commands that are there. You can learn a lot about windowing. So these are, you have put multiple windows here and you have seen how it distorts the signal. Okay, so here the distortion is less in the time domain, but in the frequency domain, the side lobes are larger as compared to this. So you can actually just go to window designer or filter designer and just play around. Just design different filters, multiply windows, multiply with the signal, see how it distorts. It's unbelievable how much you can learn by just doing this. Okay, so time's up today. We have finished windowing. We will start with multi-taper in the next class. Should probably take a couple of classes. I'll stop recording now.